My name is Goki. I'm from the National University of Singapore. I'd like to start by thanking Mercor and all the organizing members for this wonderful conference. It's been a very overwhelmingly educational week, and I wouldn't blame you if you're feeling anticlimactic in this on this last day. But I hope I can keep you entertained for this last day. So my talk is about excitons, just like many of the earlier talks this week, but nothing about Moiré excitons or nothing about interlayer excitons. My talk is about excitons interacting with point defects and how they may lead to some interesting effect. So why do we care about excitons interacting with defects? Well, first of all, because this is not something you can avoid at all. If you take many of these two-dimensional semiconductor crystals, it's riddled with a huge density of defects, sometimes Caucasian vacancies, sometimes passivated vacancies, sometimes metal impurities, sometimes some charge defects. So if you just shine light to this above the optical gap and form an exciton, these excitons will definitely interact with all these defects before emitting light. Maybe they get scattered, maybe that they get trapped. So the light that comes out of the sample doesn't necessarily contain information about the free exciton property of the system. Now, this is not necessarily a bad thing, and as many of you know, since 2015, it's been known that some defects are actually very good or potentially useful. So in 2015, a series of papers came out reporting the similar effect, where if you just take any of these 2D crystals, semiconductors, and cool it down to cryogenic temperatures, you see some very sharp emission lines here and there within the sample, probably often randomly located within the sample. And if you send these sharp emission lines, or emission from these sharp lines, to Hamburg-Brown-Tillis interferometry and measure second-order autocorrelation, you find this dip in the zero delay line, which tells you that these are single photon emitters, or they are emitters that emit photons, single photons at a time. So some defects do that, but not all of them do. And there's been a lot of progress since 2015 over the past decade. But still, we don't know exactly what it is that's trapping these excitons and giving rise to this single photon emission. So our general theme of research is to find out what would be the equivalent of an NV center in diamond, but in a 2D semiconductor. If you can, this is more of like a figurative question, but if you can find some defects like an NV center in diamond, it's not only useful, but it's also tunable and easy to handle and manipulate. So we can sort of add on to the capability of such useful defects and exploit the inherent properties of two-dimensional materials. So what would be the potential defects? The naive answer to this, for example, maybe if you have a charge defect, that can trap excitons, because if you think about the binding energy of excitons to something, that binding energy should be proportional to the reduced mass of that composite particle. And we know that free tryons, for example, which consist of exciton and a free electron, has inverse reduced mass that can be expressed as this, 3/2 times the effective mass of the electron hole, assuming that they are about the same. And we know from experiments that their binding energy is of the order of 30 millielectron volt. So if you had an exciton which encounters a charge defect, which in principle should have a infinite effective mass, then very naively speaking, such binding energy should be about 3 times greater than the binding energy of an exciton with a free electron. So based on this simple idea, you might expect that exciton bound to a charge defect should be fairly stable. Okay? But this is something very difficult to theoretically predict, and there's only a handful of papers discussing this, predicting the actual binding energy. But this theoretical paper, for example, expects that based on, similar to what we expect is based on this simple argument, that if you have exciton bound to a charged, for example, negatively charged acceptor, they will be bound to such a defect with a binding energy of about 100 millielectron volts. And the signature of that would be the emission resonance, which is located about 100 millielectron volts below the free exciton resonance. So how can we create charge defects which can efficiently trap excitons? Well, the first thing, that easy thing to do is just to create some defects. Okay? And usually the easy defects to create are chalcogen vacancies. So if you bombard a 2D semiconductor, these chalcogenide semiconductors, with electron beam, helium ion beam, or proton beam, you can easily create these defects, vacancy defects. And it turns out that these vacancy defects are indeed acceptor defects that can easily be negatively charged, so excitons can be bound to those. Okay? So this results in the emission peak, which appears really about 100 millielectron volt below the neutral exciton resonance. And actually, many of you, some of you in the audience have done already fantastic work on this, particularly by the group of Alex Holetner, where they found that if you carefully knock off chalcogens in MOS2, sulfur from MOS2, you can find single photon emitting defects. But these are not necessarily the best candidates because these vacancies can be easily be passivated by oxygen. And most of our understanding is that most of these chalcogen vacancies are passivated by oxygen. So what are the more robust candidates? Well, we believe that substitutional impurities are probably a better candidate because they are less invasive to the structure of these materials. And they are great examples. NV centers really are great examples because they do actually behave as single photon emitters. But not only that, if you just take any of the conventional two-dimensional quantum well systems and dope it with certain types of defects like nitrogen and gallium phosphide or gallium arsenide, it turns out that you get single photon emission. They trap excitons, and if you introduce these defects or impurities at relatively low densities, you get single photon emission. So the requirement is that, well, we need to find exactly what type of impurities are good for trapping excitons, but another important requirement is that we need to introduce these impurities at extremely low densities. And extremely low here means that about 10 power 8 per square centimeters. Okay, so we've been on a mission to find impurities and introducing them to two-dimensional semiconductors at desired concentrations. So there are tons of candidates, and this is actually a perfect topic for machine learning people because we really don't know exactly which is the best defect. But we started out with niobium doped into tungsten disulfide, and I'll talk about it for this. Okay, so my talk is divided into two parts. First part is, are really these impurities single photon emitters in the dilute limit? Second part, how can we even quantify these impurities in this dilute limit? Okay, so actually, if you are following the literatures on single photon emitters, you may know that, if you introduce strain, you can get single photon emitters. And you're right, but in principle, if you know exactly what defects to introduce, you shouldn't need any strain, and it would be even better because the emission should be more reproducible. Anyways, okay, moving on. So we decided to grow by ourselves niobium-doped tungsten disulfide with a precise control over its concentration. And we've developed this growth technique where we determine the concentration, predetermine the concentration of impurities before the growth by mixing the precursors in the liquid phase. So we can, by going through some dilution processes for the liquid precursors, we can control the concentration of impurities fairly well. So we grow these monolayer tungsten disulfide with niobium impurities take off the substrate, encapsulate it with boron nitride, and conduct spectroscopy. Okay, so typical samples, if you don't care too much about the concentration, what we get is something like this, doping density of about 1% or maybe 0.1%. And you can, by electron microscopy, you can identify the density fairly well. But by diluting the impurity densities, we can go to this limit, what we call quantum regime, where there's just one single impurity within the optical diffraction limit. So that's a concentration range of 10 power 8 or below 1 ppm. Okay, so what do we see? So this is the spectrum. So the pristine sample where we don't introduce niobium is this. It looks like this. We have the typical emission resonances, emission peaks that can be associated with some free exciton species. Now, if you introduce a little bit of niobium, we get, or a little bit meaning 500 ppm of niobium. We already modified the emission characteristics substantially, but we see this huge emission feature at this low energy. But we reduce the concentration of these impurities further and further, and when we approach this ppm or sub-ppm regime, we start to observe this very sharp emission lines. And these emission lines are actually not uniformly, not observed across the entire sample, but only certain locations within the sample. Okay, so since this is a sort of 1 ppm is really the limit where we start to see single emitter within the diffraction limit. We believe that these are actually coming from excitons trapped by individual niobium impurities. When we look at the emission line width of this niobium-induced emission peak, for concentration above maybe 10 or 100 ppm, we see a Gaussian emission or inhomogeneously broadened peak, whereas if you approach this sub-ppm level, we start to see emission peaks that are sub-milli-eV narrow and also Lorentzian, almost Lorentzian broadened. So we are no longer affected by inhomogeneous broadening, as we might expect from this ensemble argument. Now, we send this, when we look at the lifetime, we see that the lifetime is fairly long, but this is actually, it has multiple components. In fact, there's a background emission, which has a very long lifetime, but the emission lifetime of this sharp line is of the order of 80 nanoseconds. This is actually not so great, but actually we can use this difference in the lifetime of this background and the emission line, this sharp emission line, to understand the photon statistics of this peak. So we send this emission, the light, to Hamburg-Brown twist interferometer. And when we did this right from the beginning, in the beginning, we didn't see any photon anti-bunching as we wanted to see. But when we did the excitation with a pulse laser, we can deconvolute the components of the long-lived background and the short-lived emission line, which is a narrow one. And although it's fairly noisy, but we can see that there's a dip in this zero delay time, which suggests that these are indeed single photon emitters. Now, another question we had is, what is it that's really composing these bound states? I won't go into too much detail, but there are different ways of describing these transitions. One picture is this type of band-to-band transition. Another picture is bound-exciton complex picture. And they seem to be very similar, but really the contribution of the block states is different. So actually the degree of freedom of these emitters are quite different. So it makes sense to explore these. And that's what we did. Again, I'll skip the details, but what we did is to look at the G factor of these emitters. And when we find out, when we measure the G factor of this very narrow emission line here, niobium-induced one, it turns out to be of the order of -10, which is very close to the G factor of dark excitons. Yeah. If it were a transition from the conduction band minimum directly to this niobium state, the G factor would be much smaller because the G factor of niobium, which is composed of dz squared orbitals, is very small. So we get some idea that these are actually, what we see are actually dark excitons bound to negatively charged niobium impurity centers. Okay. Okay. In the interest of time, let me skip the details here. So the second part, I'll talk about the materials characterization part. When we are exploring the density of these impurities in the sample, in the dilute limits, we start to encounter this issue of, how do we quantify these impurities anyways? If you only have one defect over an area of maybe like several microns, you cannot use atomically resolved microscopy techniques, which would take much, much longer time. So what we did is to just simply take AFM, but measure conductive AFM, measure out-of-plane conductivity of our samples by scanning the AFM tip across the sample, which is sitting on a conductive substrate, graphite, with the hopes that we may see some conduction, enhanced conduction when the tip hits the impurity. And this is actually what we naively initially imagined, and somehow one of the rare occasions where we see what we expected to see. So on the left-hand side, we are looking at the current map of this conductive AFM scan across 100 by 100 nanometer length scale. Middle is the topographic map. So we absolutely see no topographic features of our sample. But when we see a bunch of these sharp hot spots, which corresponds to enhancement of the current by 2 orders of magnitude when the tip hits something. And when we count the number of hot spots, their density corresponds to something of the order of, in this particular sample, of the order of 10 power 10 per square centimeters, which is far less than the density of Caucasian side defects, which we know to be of the order of 10 power 13. So what we are picking up here is definitely not Caucasian side defects, or most likely not Caucasian side defects. So to verify that these are actually coming from impurities, we prepared a series of samples, measure their density by electron microscopy, count the number of these impurities one by one. This is very laborious work. And then prepared another sample for conductive AFM to see how many hotspots we see. And it seems to be there's a very nice correspondence between the densities that we see under electron microscope, which we know to be due to, in this case, vanadium impurities in tungsten diselenide, and also the hotspots in this conductive AFM scan. So we can be fairly confident that these hotspots are actually due to vanadium impurities, individual atomic vanadium impurities within the monolayer tungsten diselenide in this case. So it's a very nice technique, very simple technique that will allow us to measure, quantify the impurity densities at room temperature in ambient condition. So in the interest of time, I guess I'll skip the details of why we can even visualize these impurities individually. But it's something related to, this is actually a tunneling problem, but tunneling in the presence of some impurity-induced resonance state. And again, I'll skip the details here, but indeed, as our model predicts, there should be an enhancement of the tunneling current when the tip hits the impurity center. What's actually even more interesting is that if you have different types of impurities in the sample, sometimes we see it, sometimes we don't. So vanadium we do see. Titanium in tungsten diselenide we also see, but when we introduce chromium or manganese or cobalt, somehow we don't see them. And this is also consistent with our model because actually it turns out that, well, vanadium and titanium are the acceptor impurities that create states close to the valence band of tungsten diselenide, which actually enhances the conduction, tunneling current. Okay, so if you are working on STM, you may feel that, we could do that. STM is even better in identifying impurities. I wouldn't argue against it, but I'd like to just point out that actually really the conduction mechanism is very different, and because of that, what we are sensitive to with conductive AFM is very different as well. Okay, Okay, I think I've said enough, so I'll skip the details here, blah, 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 okay, and just directly go to my acknowledgement. So the work I presented here were led by my PhD student, Joy, and Nam, and was also done in collaboration with our NUS colleagues, and as well as our NIMS collaborator. And I'd like to put up a summary slide here, and also an advertisement for our recently published paper, which talks about electroluminescence, okay, which has nothing to do with the topic that I just shared. But anyways, thank you for your attention, and I'm happy to take any questions.
Questions? Yes.
Thanks very much. Two quick questions. One is these other non-cobalt, chromium, whatever, these are later impurities that do not show up in conduct AFM, are they still single photon emitters?
Oh, okay, so that's a good point. So for some reason, so we've studied the emission properties of all these different impurities. For some reason, many of them are not very bright. For some reason, niobium is the only one that was bright within the samples that we tested. So no, I mean, they could be, but they are just not bright enough that it's not really feasible to do the measurement.
Okay,
yeah.
Thanks. A second question is, can you comment on the magnetic electric field sensitivity, or can these emitters also be used for sensing?
Magnetic fields dependence?
Yeah, I guess some of them may have spin structure, but they have some field dependence.
So, well, I mean, so I've shown the G factor of these niobium-induced states, and they're very similar to dark excitons. So that's how sensitive it is. But definitely, what would be interesting to see is, if you can see any ODMR, just as one would see in diamond, and that's something that would be an interesting topic for the future. Yeah.
Maybe one quick question.
So in these emitters, what's the transition dipole moment orientation? Is that actually in plane, or is it out of plane? And because you're not sensitive as much to the out of plane component.
Well, because we're not really breaking much symmetry in the out of plane direction, it should be in plane, and we don't see any polarization of these emitters. So it should be very similar to what a trion is. It's just a stationary version of a trion. That's our understanding. Oh, okay. Okay. Yeah, that's a good point. Yeah. So, okay. So I guess I should say that we haven't really explored the dipole orientation in detail. So if it's a dark exciton, it should have some out of plane component. Yeah.